Hello and welcome to Physics 20, Lesson 6.1a. Concept is work. So work is often defined as, energy, is often defined as the ability to do work. And work is simply the product of force times displacement. So work is equal to force times displacement. Okay, force is a vector, displacement is a vector. Ironically, though, work is actually not a vector. Now, in order to kind of get an idea of what we're talking about here, the energy, we need to think about what energy is. And energy is really not a physical thing. We think of it in terms of stores and pathways. The energy store, uh, allows us to make calculations. It's just saying that energy is stored within this method, right? It's not a physical place, but it allows us to see what. And now each of these does have an equation associated with it. And for all the millions of types of energy, ultimately there's 8 ways in which it's calculated, 4 ways in which it is transferred along a particular pathway, right? And the energy pathway is the work that is being done. It's moving from one store to another store. Now, there are 8 actual thermal stores. There are 3 which we'll be dealing with specifically in Physics 20, and that is your kinetic store. That's stored by the object moving. Now, if the object stops, it no longer has that kinetic store of energy. It has been passed along to other stores. An elastic store, where something is squished or stretched or squashed, and the gravitational, which is due to its height. Those are the 3 we're going to be looking at within Physics 20. We will be looking at the others in other courses, but these are the 3 we're dealing with in Physics 20. Now, there are 4 pathways, but the only one that we're really going to be worried about here in Physics 20 is the mechanical one. And notice it transfers when object changes position, right? And work is the force multiplied by the displacement, the change in position. A couple of things. First of all, force must be exerted on the object, right? And this really makes sense, if work is equal to force times displacement and there's no force, well, then the work done is 0. But it also must be in the same direction of the movement. If I apply a force this way and the object moves this way, have I actually applied a force to it? Oh, not really. However, if I applied a force this way and the object was displaced this way, did work done? Well, yes, it was. What if I apply a force this way and the displacement is this way? Well, then this part, yes. That part, no. Right? At least some part of the force must be in the same direction as the displacement. And it's where these 2 fall in line that the work is done. Now, the force used to calculate the work done that should not say net force. It's actually the applied force, right? That is the actual work done. There could be other forces acting on it that are also doing work, but the force that we're doing to calculate is the one that we're applying is the work that we are doing, right? So for example, if we've got an object and it's moving along, let's say it's got friction moving along, and I'm pushing the object. But the push and the friction means that the velocity is equal to a constant, so it's not accelerating. Well, the net force would be 0, but this is the work that I'm applying to the object, and this is the work that the friction is applying to the object. And so we use the applied force to talk about the force that we're doing. I do hope that makes sense. When we take a look at units, work is measured in the joule, which we use a capital J. Force is the Newton, and displacement is the meter. And so we use these as the standard units. So a joule is simply equal to 1 Newton meter. We keep standard units because then our transference from one unit to the other, we don't need to worry about really what's going on. For example, if we use centimeters. So let's take a look at an example. We've got a 15 kilogram object that's lifted at a constant velocity from the floor to a height of 1.5 meters. How much work is done to lift the object? Well, if we think about this, it's a 15 kilogram object. In order to lift this, it's going to have to, the force that we apply has to be equal and opposite to gravity. So this will be equal to mg, but it'll be positive. Okay. We're using a distance of 1.5 meters, and work being force times distance means the force can be measured with the 15.0 kilograms multiplied by 9.81, because we assume we're on Earth, multiplied by a distance of 1.5 meters. That gets you 220 joules of work that are done. Notice again, it's the applied force that we are using to say how much work we are doing. Well, if it's moved horizontally 5 meters across the floor using a horizontal force of 3 newtons, how much work is done? Well, again, we've got that 10 kilogram object, but we're using 3.0 newtons, and it's moving a direction of 5 meters. Well, work being force times distance, we're going to use the 3 and the 5. 15 joules of work is done. Here, we're using the 3 newtons because the displacement is this way and the force is this way. We are not lifting the object, so we don't need to worry about going against gravity. Force and displacement must be in the same direction. Let's take a look at a third one. A 3 kilogram object is held above the floor, 1.2 meters, for 15 seconds. How much work is done on the object? Well, we have a force of gravity and we're holding it, so that would be the force that's applied. My arrow looks to be a little bit lopsided. But if it's being held, the displacement is 0. So regardless of how much force this is, if this is 0, the work done is 0. We're not moving it. And this may seem like an odd concept. Well, you are expending fuel, and yes, you are. And yes, you will get tired holding an object up for a long period of time. But that just means that you're not using a mechanical transference. It's going into other things such as heating, like you will get hot, as opposed to that mechanical transference. We've got a 50 kilogram box pulled 11 meters along a level surface by rope. The rope makes an angle of 35 degrees to the horizontal with a tension of 90 newtons. How much work is done? Now, remember, the force must be in the same direction as the movement. So if it's a 50 kilogram box. We've got a 90 newtons at 35 degrees. If it's sliding along this way, 11.0 meters, then we need to know this portion, not this portion. That's actually check mark and an X. So to find the horizontal component of the force, that is going to be 90 cos 35. Which means the force being applied in that direction is 73.7 newtons. So now the work done is just force times the displacement. That's 73.7 newtons multiplied by the 11 meters gets you a total of 811 joules of energy. Okay, and again, that's this idea of direction and force must be going in the same plane, in the same pathway, same direction. So at this point, pause the video, give this one a try, and let's see how you do. Okay, welcome back. Again, you've been given a weight of the box and you've been given a tension on the box. It's the tension we're worried about as we're pulling it along, but we need to make sure that the force is in the same direction, and you should have wound up with 303 joules. Now, if we've got a car moving, a 1,385 kilogram car traveling at 61 kilometers per hour, brought to a stop while skidding 42 meters, what's the work done on the car by the friction between the road and the tires? Well, if you remember Newton's second law, F is equal to ma, what we're really needing is the acceleration and multiply it by the mass in order to get the force, and then we'll multiply it by this 42 meters. Now, 61 kilometers per hour is not standard units. We're going to change that 1,000 meters per kilometer, and 1 hour is 3,600 seconds. So it's actually 16.94 repeating meters per second. That is your initial velocity. Final velocity is equal to 0 because it comes to a stop. We know the distance of 42 meters. We're looking for the acceleration. So we'll use that Vf squared is equal to Vi squared plus 2AD. So 0 squared is equal to that 16.94 squared plus 2 times A times 42. Moving this over, you get negative 287.1 is equal to 2A42. Dividing by 2 divided by 42 means the acceleration is negative 3.42 meters per second squared. And work is equal to force times distance, which means you're really just multiplying by 42. To 3 significant digits, that's 144 joules of work done. Notice work is not a vector, so we're not worried about the direction with that acceleration. Oh shoot, you know what I forgot to do? To find force, it's mass times acceleration. So when we do the force times distance in ma, work is equal to mass times acceleration times displacement. Yes, work is mass, so we need to actually take the 1,385 multiplied by the 3.42 multiplied by the displacement of 42. That gets you work done being 1.99 times 10 to the 5 joules. Quite a bit bigger than what I had over there. My mistake. Almost forgot the mass of F equals ma. So, if you have any questions, please let me know. Otherwise, have a great day.